As the name suggests, the fundamental theorem of calculus is an incredibly important central theorem to pretty much all of what calculus is about. Now, we talked about the derivative and how that is an important concept, and we've also started to talk about integration, and we have alluded to the idea that they are connected through the concept of an antiderivative being an indefinite integral, but we have yet to formally kind of unify them into a single concept here. So that's what the fundamental theorem of calculus does. It gives us an official kind of unification of the concept of differentiation and integration. And it breaks down into two parts. The first part gives us that official kind of unification. The second part is actually going to be more important to us computationally. It will help give us a way to use that unification to help evaluate integrals in a much more efficient manner. I mean, let's face it, Riemann sums are very, very inefficient. Whether we are doing them repeatedly with increasing values of n, or whether we're just going straight to the unspecified value n with a limit, it's a lot of algebra. It's a lot of writing. It's a lot of work. It would be nice if there was some better, more efficient way to do it. And there is, and the fundamental theorem of calculus will give that to us. So first, we're going to start with the idea that, as usual with integration, we need a function that is continuous. So we have f is continuous on an interval from a to b, and then we have some value x within the interval, somewhere between a and b, including a and b itself. So we have a function continuous on an interval, and somewhere in the middle of the interval we have another x value floating around. So as integration does, it finds one of the definitions of it, a definite integral in particular, finds the area of the region bound by the graph of a function and the horizontal axis on a certain interval. Now notice here, I didn't do the full interval from a to b. The area of the region bound by the graph of f and the horizontal axis on a to x is a function of x. The idea is that x is floating between a and b. X can be close to a, it can be close to b, it can be right in the middle, or anywhere else. So since that value of x can change, the amount of area that we get will also change. And what we get then is an area function, a of x, and it is equal to the definite integral from little a to x of f of t dt. Now, we can't use the same variable for multiple things. Since x is defining the upper limit of integration, we can't use it as the input variable for f. So we use this other variable t. That's why I said the horizontal axis and not the x-axis, because the input variable to f is t, so that x can be defined as a specific value on that axis. But this is what's known as the accumulated area function. It's based on the idea that for a function, and just to make things easier, we'll keep the entire function positive. For a function on an interval from a to b, the amount of area we get is going to be determined by how far along we integrate. If we integrate from a to x sub 1, we're going to get 1 bit of area. But if I put my x value somewhere else, then I'm going to get all of the area I had before plus more. And if my x value goes to yet another place, I'll get, again, all of the area I had previously plus another section. So the amount of area I have is going to be determined by how far along I integrate. Now the interesting thing is that the accumulation of area is smooth. What does that actually mean? Well, think about where we've used that phrasing before. We've used it to talk about when a function is differentiable. In order to be differentiable, it has to be a smoothly progressing curve. It cannot have any abrupt changes in slope, like you would see at a corner or a cusp. It has to be continuous. It can't have any discontinuities. That, again, would be something that is not smoothly progressing. It also can't have any places where the tangent line becomes vertical. So it has to be a smoothly progressing function with no funky kind of points. Well, if we look at the accumulation of area here, we get the impression that that's exactly what's happening, is that the accumulation is smooth. We don't have an abrupt jump from, say, an area of 10 to suddenly an area of 20 without hitting anything in between. It's a smooth accumulation, and therefore the area function is differentiable. And here's the interesting part. The derivative with respect to x of the integral from little a to x of f of t dt is actually equal to f of x. Well, what does that actually mean for us? What it means is that basically we've got this function f, and we're going to do an integral of f, and then as soon as we're done with the integral, we're going to do a derivative. And when we do that, we get right back to where we started. That is the very definition of inverses. Inverse operations, inverse procedures mean that to do one and then to immediately do the other afterward should land you right back at where you started. So if we start with the function f, integrate it, and then immediately differentiate it, we get right back to where we started. What this tells us then is that definite integration and differentiation are inverse processes of each other. They are inverse processes of each other. This first part of the fundamental theorem of calculus unifies the concept of a definite integral with a derivative. Now, they are not perfect inverses, meaning that much like a square root and a square, the order in which you do them matters. If we take any x value in the world, any number we can think of, be it positive or negative, zero, fraction, decimal, whole number, any possible number, if we do the square of it first and then follow up with the square root, they do not necessarily come out the same. If we choose a positive value or 0, they do. Because if I say square positive 5, I get positive 25. And then when I go to do the square root of positive 25, I get back to positive 5. But if I were to start with a negative value, say negative 3, when I square negative 3, it becomes positive 9. And then the square root of positive 9 is not negative 3, but positive 3. So they are not perfect inverses because they don't work on any x value in the world. We have to observe a certain restriction. Now, as long as we observe the restriction, they can be done in either order. But the fact of the matter is that if we do that, if we square first and then square root, versus if we do a square root first and then square, one way works perfectly, the other way not exactly. We get that same effect here. The integration has to happen first. And the reason for that, and part of that is what we'll get to see when we do the second part of the fundamental theorem of calculus. Integration, as we've seen, through antidifferentiation, always produces the constant of integration. So when we would integrate, we would get the antiderivative plus c. So integration kind of introduces this new term that wasn't there previously. But when we differentiate it, that term is a constant. Differentiating that constant means it's going to drop to 0 and disappear. So integration creates new information, and then differentiation destroys it again, which works out fine as long as we create it first and then destroy it. The thing is that differentiation destroys, and once we've destroyed something, it's very difficult to recreate it. So if we differentiate first and destroy a constant term, integration is going to have a hard time recreating it, as we've seen. Integration can recreate a constant term, but we need to know specific point, an initial value as it's called, a specific point on the antiderivative. So that doesn't exactly cancel out perfectly. They're not perfect inverses in that way. Integration has to happen first, and differentiation can happen second, and in that way they are inverses of each other. Now, how does this first part of the fundamental theorem of calculus work? Well, we might be given a function such as a of x is equal to the integral from, say, 1 to x of t squared plus 3t minus 4 dt. Now, the idea is to find a prime is that we would have to do the derivative with respect to x of this integral from 1 to x of t squared plus 3t minus 4 dt. Now, I suppose what we could do here is we could evaluate this using a Riemann sum. We could do that, but that's a lot of work. That would actually be an excessive amount of work, especially given that the interval has an unspecified right bound, because it's from 1 to x. It'd be much easier if it was, say, from 1 to 3 or 1 to 8. We would know the upper bound. Since we don't here, that would make this definitely more difficult. On the other hand, the fundamental theorem of calculus, the entire idea of it, this part of it anyway, is that we don't have to actually evaluate this. We can use the idea that the integral followed by the derivative cancels out. And what we should get then is simply the integrand in terms of x. Without actually doing any work. Interestingly enough, we don't actually have to do the work here to do this. The derivative of a definite integral is the integrand in terms of the variable x. An interesting point is that it doesn't actually matter what the lower limit of integration is here. The fact that I started integrating from 1 does not actually affect this. I could have started integrating from 2, or from 10, or from -4. As long as the function is differentiable, as long as the function is continuous on the interval that I'm working with, then there is no problem whatsoever. and I'll get the same thing here. Now, that's nice, and it's cute, but it doesn't really do much for us as calculus students. So, the part of the idea of calculus, and if you listen to the word calculus, it has the same root word as calculation. Calculus is about computation. So that first part of the fundamental theorem of calculus is nice, and it formally unifies the concept of definite integrals and derivatives. But as far as computation goes, it's not really doing much for us. It would be much more helpful if you were, say, a math major and you had to write proofs and whatnot. That's not what we're here that's not within the scope of this class, and that's not what we're here for. So it's this second part of the fundamental theorem of calculus that's going to be much more important to us. The second part is going to unify now the two separate definitions of integration. The idea that there's an indefinite integral, which it deals with the antiderivative, and as we just saw, the definite integral, which deals with area, and the definite integral is already tied to differentiation. So if we can now tie those two things into the indefinite integral, the antiderivative, then we'll have all three things: the derivative, the definite integral, which is area, and the indefinite integral, which is antiderivatives, all grouped together through these two parts of this theorem. So let's start with little f being continuous. Again, necessary for both differentiation and integration. Let f be continuous, little f be continuous on a to b. And we're going to let big F be any antiderivative, meaning we do not actually need to specify the constant of integration. All we need here is the idea that the indefinite integral of little f is going to give us big F plus some constant of integration. In that case, the definite integral from a to b of little f of x dx is actually equal to the general antiderivative big F of x plus c evaluated at the limits of integration and subtracted. So we take the antiderivative big F of b plus c minus the general antiderivative big F of a plus c. And an interesting thing happens here. The constants of integration actually, and this is why we say big F can be any antiderivative, the constants of integration are actually going to cancel out exactly. So what we have here is that a definite integral can be evaluated using the antiderivative. The general antiderivative, we don't even need to be concerned with finding out the value of c. Whatever the value of c is, it would be the same when we evaluate at b as when we evaluated a, and therefore would cancel out. So whichever antiderivative we're using, that constant will always cancel out, and therefore it's not something that we actually need to bother finding the value of, interestingly enough. Now that does tie into what we said back here about how the lower limit of integration is actually not important to this part of the fundamental theorem of calculus. The lower limit of integration here was not important, and it ties into this here in the idea that the lower limit would affect the value of c. Where we start accumulating from would affect the value of c. But as long as it's consistent for the antiderivative here, as long as the constant of integration is consistent for both x equals b and x equals a, then it doesn't really matter where we started accumulating from. It will cancel out either way because both things started accumulating from the same place. What does that actually mean? Let's look at a simplistic example. This is the function f of t is equal to 60t. Oh, excuse me, 60. Excuse me. F of t is equal to 60. We can think of this as a velocity function. We can imagine this as a car traveling at 60 miles an hour a constant 60 miles an hour. Imagine they have the best cruise control in the world. F of t is actually the velocity function for the car, constant 60 miles per hour. Now, we know from dealing with antiderivatives that if this is the velocity function, then its antiderivative should be position. So, if we were to simply find an antiderivative function, a general antiderivative, it would be the integral of the constant 60, which would give us 60t. Now, I'm going to leave off the constant of integration for the moment, and we'll see why in a moment. The constant of integration here could actually, well, again, from having dealt with this in a previous lesson, the constant of integration can easily be determined to be 0 based on the idea that the initial velocity, well, I guess it gets a little hairy there. See, when you're driving in a car, you have to accelerate up to 60 miles an hour and then set the cruise control. So it's hard to say the initial velocity was 0 because we're not actually seeing that acceleration at the beginning. We're really just seeing the 60 miles an hour starting from the moment we set the cruise control. But if we look at everything from that point of view, at the moment we set the cruise control, we haven't actually driven anywhere yet. We're in the car and we're driving, but if we're counting everything from just that moment, at the exact instant, we haven't traveled any distance yet from the moment we set it. So in that way, we can interpret the initial position as being 0. It requires a little bit of careful manipulation of what we're dealing with, but it does work. Now that being said, this position function should work just fine. So, for example, if I wanted to know how far have we traveled after, say, 7 hours, well, we could simply do S of 7 is equal to 60 times 7 and get 420 miles. This works just fine if we come up here and, actually, if we were to, say, find the area under this curve. This would be a rectangle now that has a width of 7 and a height of 60. 60 times 7 is 420. Now, that works out just fine, and we could use any t value we want for this. What if we change the question, though? how far do we travel between t equals 2 and t equals 5 hours? Now that's, again, I chose a simplistic function, and this should be an easy enough answer to come up with just from a little bit of common sense. From t equals 2 to t equals 5 is 3 hours, right? So if we're traveling at a constant 60 miles an hour, 60 times 3 would be 180. Now, the interesting thing is, though, that if I try to do just straight out s of 5, I don't get the right value. I get 300. And if I try to just do s of 2, I again don't get the right value. I get 120. However, it's easy to see that the proper amount of distance traveled in that time period is simply the difference between these. So what we're looking at is the region from t equals 2 to t equals 5, and we want this area in between. We can interpret that as the definite integral from 2 to 5 of our velocity function. And that would give us our position function evaluated at 5 and evaluated at 2. And this would give us exactly the subtraction we need. Excuse me. This would give us exactly the subtraction that we need to produce the 180 we're supposed to have. Now, the idea here, and again, the reason that we don't need the constant of integration here, is that these are kind of both based off of the same starting point. They're both based off the idea of starting at time 0, t equals 0. The idea is that the 60 times 5 is actually finding the area from 0 to 5. It's finding the total distance traveled at the 5-hour mark, and then subtracting out the first 2 hours of it. So it's really what it's looking at is a shared starting point of 0. And as long as the two things are sharing that starting point, the actual value of the limit of integration is irrelevant. For example, another example here, what we can do is instead of looking at 2 to 5, we can look at another 3-hour gap. What if we only start the cruise control at 2 hours? What if the first 2 hours were all kinds of different speeds up to that, and 2 hours is the point at which we set the cruise control? What if we then ask about the distance traveled from t equals 4 to t equals 7? Well, in this case, it wouldn't really make sense to talk about the distance, to talk about from time 0. We would really need to start by talking about at time 2. But again, as long as we're using the same starting point, what we've got here is from 2 to 7 is still a distance of 5, and from 2 to 4 is still a distance of 2. So we're still looking at a 3-hour period of time, and that should still be 180 total miles traveled. It's just we're starting from a different point. So, interestingly enough, we get the exact same result here, But we have to ignore those first 2 hours where we weren't traveling at the constant velocity. So the idea is again here that it's not the starting point that matters, it's that we have a common starting point between the two integrals, really, that we're looking at, between the two values that we're evaluating the antiderivative at. Now that seems admittedly a little bit vague and confusing. So let's look at this with an actual problem that we would have seen in a previous lesson with the Riemann sums. Through the Riemann sums, we went through a function f of x equals x squared on the interval from 0 to 2, and we did it with increasing numbers of subintervals until eventually we got to the idea of using a limit. And that took, 5 videos to go through, and well over an hour's worth of time and work in watching those videos and working through everything. We can do the same thing much, much more quickly here. What we're looking for here is the area of the region on the interval from 0 to 2 of the area bound by the graph of x squared and the x-axis. So what we're looking for is the definite integral from 0 to 2 of x squared dx. Now again, what we could do is the Riemann sum. We could do a delta x equals 2 minus 0 over n. We could do an x sub I equals 0 plus 2 over ni. And we could turn this into a limit as n goes to infinity of the summation from 1 to n of 2 over ni squared times 2 over n. And we could do that whole thing. But again, what we've seen is that is an extended process with a lot of algebra, a lot of writing. And this one isn't even all that bad, as we saw, because starting the interval at 0 really simplifies the expression a lot. And we are dealing with a pretty simple function, just x squared. So this one isn't even all that bad, and even then, this is a lot of work to have to go through all of that with the summation formulas and whatnot. What if we could just do the antiderivative of x squared evaluated at 2 and at 0? And the antiderivative is simple enough to get. We can do it with the power rule. We add 1 to the power and divide by the new power. So then we evaluate it at the upper limit of integration first, and then subtract it when it's evaluated at the lower limit of integration. 2 cubed is 8, and 0 cubed is 0, so we have 8 thirds minus 0 thirds is 8 thirds, which is the value we got when we did this the very, very long way using a Riemann sum. Except now we can do it a great deal faster. Let's do one more example. Again, this is from one of the Riemann sum videos. After going through that whole extended process of developing the limit definition of the integral, we then turned to a new function on a new interval and did it there. So let's take a look at that function here. We have on the interval from 1 to 4, the area under the curve of negative x squared plus 2x plus 8 dx. Now again, we could do the full Riemann sum, but that seems a little bit ridiculous. The idea here is to do the antiderivative instead. Now again, through properties of the antiderivative, we can do the antiderivative of each term separately. The antiderivative of negative x squared, well, the negative comes along for the ride. That's just a coefficient. And then the power rule, we add 1 to the power and divide by the new power. Very much the same thing for 2x. The 2 comes along for the ride. And then for the x, we add 1 to the power and divide by the new power. And then for the constant, well, the antiderivative of a constant is a linear function. We can clean that up just a little bit. We'll make this, again, negative x cubed over 3. We can let the 2's here cancel out so that we just have plus x squared. And then plus 8x. And now we evaluate it at 4. So we have negative 4 cubed over 3 plus 4 squared plus 8 times 4 minus the antiderivative evaluated at x equals 1. Negative 1 cubed over 3 plus 1 squared plus 8 times 1. And the rest is just cleaning it up and doing the arithmetic. We have negative 64 over 3 plus 16 plus 32 minus negative 1/3 plus 1 plus 8. Now, I suppose what we could do is get a common denominator for everything, but if we're observant here, we might notice that the two fractions are actually going to combine and simplify down to a whole number. So we're going to have negative 64 over 3, and from distribution of the negative here, we're going to have plus 1/3, and then we have plus 16 plus 32 minus 1 minus 8. And when we combine these two fractions, it becomes negative 63 over 3, which is just negative 21. And then combining these, well, that's easy enough. The 16 and the 32 together is positive 48. And then for the negatives, we have negative 21, negative 1, and negative 8 is actually negative 30. So this whole thing comes down to be positive 18, which matches the same answer we got when we did this with the much more extended Riemann sum, which again, in this case, would be much bigger of a pain in the butt than, say, the previous example. Our interval starts at 1, which means our x sub I formula is a binomial. It's a larger expression for the integrand. It's not just a single term of x squared. It's an x squared with a negative in front of it, and a 2x and an 8. So there would be considerably more algebra to work through with the Riemann sum. Even this, which did have, kind of a bit of writing in it, none of it was nearly as complicated as a Riemann sum would be. So we have this now, the second part of the fundamental theorem of calculus, which allows us to evaluate a definite integral by finding the antiderivative and evaluating the antiderivative at the two limits of integration. Now, I will caution you here, this is subtraction. The order of subtraction matters, so you have to pay attention to which limit of integration you're putting in and which order you're subtracting it. If you subtract it in the wrong order, you get the wrong answer. So be very careful with the order of subtraction, but otherwise, it gives us a much faster way to be able to evaluate definite integrals, and actually a much more useful way because we have a greater capacity to find antiderivatives than we do to use a Riemann sum. The Riemann sum is unfortunately limited to our ability to use summation formulas, which is limited to polynomial functions of degree 3 or less. What if it's a trig function? What if it's something else that is not a polynomial? Now, that doesn't mean that there's no way to do it. It just means that the Riemann sums aren't going to work. But we have a better capacity to find antiderivatives. We do have antiderivatives for the trig functions. We do have the capacity to find antiderivatives of, say, a square root function, or 1 over x, or exponential functions. We do have that capacity. So this is not only a much faster tool, but it's much easier to apply because we have a broader capacity for antiderivatives.